right. So good morning, everyone, and welcome to the JKMRC Friday morning seminar series. On behalf of the University of Queensland and the Sustainable Minerals Institute, I'd like to acknowledge the traditional owners and the custodians of the lands on which we meet today. We pay our respect to their ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contributions to Australian and global society. And for this seminar, it is my pleasure to welcome Professor Nick Cook. Nick commenced his geological journey at the University of Otago in New Zealand before moving to teach and complete a part-time PhD at the University of New England in Armidale. Nick had an industry exploration career in Eastern Australia, followed with time living in Broken Hill, Parkes, and Brisbane. Following a non-geological interlude, Nick then worked as a consulting in Australia, Southern Africa, and Europe, with his time mostly occupied in northern Finland as the technical lead on the discovery of the Rajapalot gold-cobalt resource. He moved to SMI in October 2022 as the Total Deposit Knowledge Group Leader. Today, he will present a seminar titled Recognition of Multistage Gold and Cobalt Mineralization in the Finnish Paleoproterozoic, Advanced in Geoscience in Discovery. So let's give a warm welcome to Nick. Thanks, Nick.
Good morning, everybody, or afternoon, or in future online. Welcome. You may or may not know that I've been involved in this work since 2012, and I'm going to lead you through a discovery process that I was not on the team at the time, but arrived a couple of years after. And I'd like to give you an insight into what sort of, I suppose, cool geoscience we can use in the day-to-day discoveries and, I suppose, manipulating how you can actually go about improving your results in exploration. So what are we going to do? A little bit about the location. We'll talk a bit about project generation and why we went to where we are. We'll talk about uranium and gold, great topic, somewhat controversial at times, depending on what part of the world you live. We'll talk about how we actually dated the components of that system. And then we'll move on to the second part of the discovery process, where we found a gold and cobalt resources. And then we'll look at how those relationships between the gold and the cobalt actually play out. We won't go too much into metallurgy other than to say it's complicated, but I will show you some geometallurgical slides to give you some indications. And then we'll try and wrap it up with time for questions. So where are we? We're up here in northern Finland, and European map here. This was probably made when the UK was still part of Europe. We went up to review the project in 2012, and then in 2013 I moved to Helsinki with the family, and then they decided that learning Finnish and living in Helsinki wasn't going to be their future, so I then commuted for the next 9 years and spent an awful lot of time on a plane. There are significant deposits in northern Finland, in particular Agnico Eagle's Kittilä or Suurikuusikko deposit, which is around 10 million ounces overall. And it's a couple of 100 kilometres to the north of the discovery that we will talk about, which is known as Rompus or Rompus Rajapalot. There has been a new discovery just recently out to the north of us called Ikkari, which looks like that's going to be about 4 million ounces as well, which is a great piece of work. It's a beautiful place to work, sometimes a little colder than here, so I have set my own internal record of going from +40 to -30 in 36 hours, which is quite a shock, but it has its moments, and when the sun's out and it's clear, it is rather beautiful. And that's actually a drilling rig hiding in the forest there. So why did we end up in Finland? So the company I worked for was called Mawson, and they were actually in this uranium boom in the late 2000s, and they thought that they would look at a project that Areva, the French uranium company, had been working on up there. And Areva was there because of the fact that northern Finland contains rocks that host the Great Oxidation Event, so highly oxidized rocks, the time when uranium was mobile in groundwater. And moreover, there were lots of reductants adjacent to these oxidized and saline rocks. So there were evaporites, oxidized red beds, and then a whole bunch of black rocks. And so if you know anything about uranium, you basically want to carry an oxidized fluid and hit a reductant. So they had a model that was based on a deposit just to east, across into Russia, where they could see these sorts of processes going on. And so they sent out explorers into actually Areva all over Finland. And one of the reasons that Areva left there was they became fairly unpopular. I can probably say this out loud. Surrounding the capital city with exploration permits for uranium is not a popularity move. And it didn't go down particularly well. So there's a whole bunch of hot granites all around Helsinki, but they also held some exploration tenements of a certain type up to the north here. And so Finland's dominated by a whole bunch of Archean rocks and Paleoproterozoic. So the Archean Paleoproterozoic boundaries are about 2.5 billion. So we're looking at rocks above and below that. So the Paleoproterozoic extends from 2.5 billion down to about 1.7-ish billion years. And if you think about gold, there is also at this time period quite a lot of gold on the planet. And so in terms of global exploration, going for rocks where there is a predominance, I suppose, of gold producing events is important. And there's this big patch in here called the boring billion. And so, you know, if you're in the project generation world, you tend not to be in that part of the world. So, and smart thinkers have put together the continents at that stage and show where all of these big deposits are. So a place like Homestake in South Dakota, 40 million ounces, so very significant ore deposits at quite high grade, so 6 or 7 grams per tonne. Highly profitable, but really, really, really hard to discover. In fact, Homestake only found their last 10 million ounces as they were about to close from an underground drive. And that says something about how hard these things are to actually find. So Finland was chosen, has great public data sets, including radiometrics. And part of the program went on in this belt called the Peräpohja. So Sweden, Norway, Russia out this side. And these green rocks here are the Paleoproterozoic that we're interested in. And these ones out here are extremely low grade for those sort of rocks, in that you can still see fossil oil at about 2 billion years old. And you can see them as desiccated tar balls in the sand. So great reductants if you're out there looking for uranium. So out went the Finns and working for the French at this stage, out with their spectrometer. And there were locations where the spectrometer actually went off scale at 64,000 counts, where there were slugs of uraninite this big in the ground. So quite spectacular. And the young geologist at the time rang his boss, who was standing here, and said, "Oh, there's not only uraninite here, there seems to be gold veins all through them." And so they went, and the very first gold pan, when Mawson went to look at this project from above one of these locations, looked like that. And in outcrop, there is gold like this. I do not know anywhere in the world where you can use your foot as scale for taking photographs of gold in outcrop. But of course, if you're a geostatistician, then nuggety gold equals problems. You just want it to be as big as that everywhere. So trying to work out what's going on is a little bit hard. So what do these rocks look like in the field? Well, the uraninite and the gold within them actually sit within a variety of folded calc-silicate veins. So these veins have dolomite, the calcium magnesium carbonate, and calc-silicate minerals because they were metamorphosed and deformed. And then within that, you find little spots of uraninite. So when you go along with a spectrometer, it makes lots of noise, and lo and behold, you find some. So they drilled the 11th hole and found Finland's best gold intersection, 6 meters at 617 grams. And this meter interval ran about 3,000. So this is mafic rocks with a vein of calc-silicate, carbonate rocks with gold. There was a hole drilled a couple of meters away that got below detection. So that straight away is an alert that this nuggety problem, although it's a great gold producing event, is going to make predictability somewhat difficult. And if you walk around in the field and you find these veins, these are foliated mafic rocks, you find these veins and notice there are fractures running backwards and forwards. And if there's anything I want you to take out of this whole seminar, it's that the tiny things can make a big difference to your overall interpretation of the project. And you'll see that as we go through. So zooming in on that square, within this piece of dolomite is a big hunk of uraninite, and there are little gold veins passing across just within the uraninite. So we have gold and uraninite within carbonate. If you look at these fractures in detail in other places, you find that they are quartz plus or minus tiny bits of carbonate, but they also contain sprays on the fractures of tourmaline. So these rocks are actually, the fractures are hot enough to precipitate tourmaline, borosilicate. It seems weird, but the tourmaline story is also littered through this whole discovery. So if we go down now and look at a piece of drill core in detail and a couple of polished thin sections, we can see here that the dolomite vein to the top and the biotite bearing amphibolite rock at the base, but within here are a bunch of carbonaceous nodules. So there are carbonaceous nodules within here. And if you're trying to precipitate uranium, remember, we want to have a reductant in the system. But it does seem weird to have organic material inside mafic rocks, inside basalts. If you go in even more into this system and start looking at what's going on in here, you see a number of minerals. Now, most of these, or some of these I've never heard of, but so the main one here is uraninite. We have gold veins within here. We have pyrobitumen surrounding the uraninite. We have galena, lead sulfide. We have altaite, lead telluride. We have nickeline, which is a nickel arsenide cobaltite, cobalt arsenide, and up here, the mineral that I sort of love the name of, hunchonite, which is a lead gold alloy. Now, the cool thing about uraninite is that you can actually date it because uranium lead decay series, but also all the other lead bearing minerals here you can date because of the lead-lead method. You can actually work out what the lead isotopic ratio is and calculate the age of the rock. So if we come and look at the age of the uraninite, this uraninite, then these large grains, is generally around 2.06 billion. As the grains get broken and get smaller, they range down to 1.7 billion years old. So they are recrystallizing, they are losing their lead, the radiogenic lead is being lost. And what's more, if you look at the minerals in the veins here associated with the gold, so we have a lead telluride, a lead gold alloy, and galena, you can date those and they all seem to come out at 1.78 billion. So they are more than 200 million years younger than the large uranium grain, uraninite grains. And what's more, if you carefully go towards the margins of these veins, the radiogenic lead disappears to zero. It has all been sucked out of the grains by the late veins in here. All of the radiogenic lead inside the uraninites have gone into those other lead-bearing minerals that are associated with the gold. So the age of the gold in those veins is actually over 200 million years younger than the formational age of the uraninite. And if any of you follow the argument about the Witwatersrand about whether or not the gold and the uranium comes at the same time, you will know what I'm talking about, but you can park that argument because some people certainly don't agree that they're apart. One of the other things I'd like to show you here is just to go back here and look at this, because there is more than one stage of gold mineralization. These pyrobitumens here are actually here because of the uraninite. There is this function called radiolytic polymerization. So in the oil field, guys, when they see monazites and stuff like that, often you see oil coating around the monazites because the radiometric decay or radioactive decay process actually grabs the oil. And that's actually what's going on here. But bizarrely, these host rocks are at amphibolite facies. So they've been heated up to, say, 400 degrees. If you do the equivalent of vitrinite reflectivity on these rocks, that pyrobitumen has only been to 250. It hasn't been cooked to high temperature. So bizarrely, that pyrobitumen and the gold and the 1.78 event is all post-metamorphic. So somehow, post-metamorphic, there is oil getting into these rocks somehow. It's a weird story. When you go over the border to the east, you do find veins of this oily material or shungite cutting across mafic rocks. And there are other places here where the rocks are less deformed where we see that also. So a great discovery. But as luck would have it, nature got in the way. That there's a 6-kilometre ridge of this outcropping gold material, 6-kilometre strike length. And because of all the dolomite veins, the soil is alkaline. And so one of Europe's rarest orchids grows exactly in the same place as the gold and uranium. So drilling that, because it was under a special type of nature permit, was next to impossible. Never mind the fact that it was very, very nuggety. So we all stood back from this, having drilled 84 holes, and said, where do we go now? Because the issue was that we had a great gold flux through these rocks, but no continuity, and probably very little chance of ever doing anything with it because of the rare orchids. So throughout the area, which was about 10 by 10 square kilometres, we had over 100 samples carrying more than 1 gram per tonne. most of those were in boulders. The whole countryside is glaciated, but much of it came from, most of it was in boulders, but some of it was in outcrop. So there were a couple of locations where we had actually got outcrops with gold within it. And this is what the country looks like. And the Finns' field geology was absolutely superb. They rolled the moss back from every single boulder. We used LiDAR data to find the boulders in the trees, and everybody carries a spectrometer. So whenever you go past anything with a bit of uranium or even potassium, it will start beeping. But it's like northern Canada, pretty flat, swampy, although not as many bugs. And this from the air is what this area looks like. This boundary here marks the boundary between forested and unforested areas, and it's actually a commune or local shire boundary. Unfortunately, to the left side here, it is Natura 2000, which is designated by the EU as an area which, if you develop, you need to take special note, I suppose, of the nature. And so with that in mind, you would have to purchase other areas as a land swap or something like that, but it doesn't prohibit it. Of course, the discovery would then happen to be, that star has moved a centimetre or so, in the trees on the wrong side of that border. And the result of that is you could only use hand portable equipment. So in order to get in there, we dragged in what's called a winky drill, a little drill that would drill 25mm diameter holes. And with our very first hole, because the first two test runs were outside, we discovered gold in a rock that at the surface contained 80 grams per tonne. And it was this weird magnesian amphibole rock. It's weird in anybody's language, never mind if you're not a geologist. But it had tourmaline, pyrrhotite, and full of calc silicate. And then all over the place, we kept on finding tourmaline and gold and visible gold in these tiny drill holes. And when you looked at the grades and told the market how wonderful the grades were, everybody was excited. So the classic open at depth gets put on your cross section, and we were struggling though to drill 25mm holes. We upgraded our rig slightly. We managed to get it to drill to 140 meters, and we made our own little spear so that we could try and orient the drill core to try and get more information out of it. But believe me, 25mm is not much to work on. So we came about this process where we argued that hand portable meant you could lift the parts off the truck and build the rig on a sled. And we got up to NQ2 or 50mm core, and we drilled some more holes. And lo and behold, when you go down dip, the results looked like that, which, you know, it's a classic exploration problem that the cross-section is only a part of the story, because if there's any linear component that's not immediately down dip, you're going to struggle. So we started drilling, and we drilled about, what did we drill from hole 25? So we drilled another 20 odd holes with that drill system and found a few bits here and there, but we're really struggling under the till and under the snow to work out where to go next. So at this stage, we had all of these gold targets within a 10 by 10 kilometre area. The Rompus style mineralisation, that was the first uranium gold stuff I showed you, hosted by calc-silicate carbonate veins with minor oxidizing alteration. The gold had two associations, uraninite gold and pyrobitumen gold uraninite. This second group of mineralisation we found had these weird, unusual magnesium-rich rocks and calc-silicates. And at that stage, I thought they were evaporites. Since changed my mind about that. And we were in an early stage. And, you know, we were pretty excited, but we were really struggling to find continuity, even though it looked so good. We were slowed down by access issues. With the licensing, the process is very slow, but we got there. So we had a bunch of friends, academics, geology, maybe geology, I never know whether it's science or not, but at least we try and persuade ourselves that it is. We had people from the GTK and we had people from universities and we had combined projects across Europe that we put to task to try and solve where to go when we had all these nuggety golds, until we eventually got to the stage, by the time we got to this hole, number 93, where we got a result that was over 30 meters at 9 grams equivalent with cobalt. And the continuity was excellent. So if you know much about gold variography and gold continuity, those gold numbers there represent an excellent chance to have some continuity. They were consistent, they were reproducible on half core, they were reproducible on pulps, everything. So the statistics behind the gold looked great. And I have to say, this moment, an absolute call out to the Finns and the way they look after their drill core, because it is immaculately clean, it's all oriented. You could go back to any piece of core. All the audits we had done have just been fabulous. So call out to all the geos and everybody else who's worked on this project, because it's not just me, of course. So we got involved in projects, new exploration technologies, a couple of other EU-related projects, and in particular, Professor Ferenc Molnar and others at the GTK. And we started into trying to delve further into the problems. So in terms of big data, we had data at all scales. We had aeromagnetics at 200 and 100 meter flight. We had some very early drone magnetics. There's a big group called Radii that have been doing this. The main problem with the drone magnetics there is that the trees get in the way. The ideal flight height would be 20 meters, but the trees are up to 40. And then we have a whole lot of skied ground magnetics within that area. We also have heliborne VTEM. And, you know, geologists drill the big dot. Unfortunately, the first big dot was 60 meters of pyrobitumen and graphite. So all this beautiful looking organic rocks with flakes of molybdenite, weird vanadium, chromium, all sorts of weird stuff inside it, but full of sulfides, 10% sulfur, 10% carbon organics within this. What we didn't know at that stage, after we drilled holes 1 and 2 with the big rig, was that all of our ore deposits that make up 1 million ounces gold equivalent lay essentially along strike from that spike. And when you get down to the nitty-gritty, just like we talked about with the hosts to the romper stuff, the rocks are tightly folded, foliated, highly deformed. And if you look at where we've drilled, this is a map of the drill traces here for the discoveries. And what's bizarre is that when you look at these rocks, you actually see that although the main fabrics are like so, east-west here for this one called Raya, which we'll concentrate on, that the trend is oblique to that. So there is actually an oblique plunge across. So it's not down dip, anything like that. It's actually across the foliation surface. And that is actually hard when you're trying to build the three-dimensional models. And this is how those models actually look here as wireframes. So the one we were just looking at is Raya, and they extend round what is probably a large overturned fold in here, and all of these red dots here represent the intersections. So we got to a stage of 10.9 million tonnes at around 3 grams gold equivalent with cobalt and gold. So the cobalt story is complex. The cobalt and the gold, I'd like to persuade you, also have that 200+ million year gap. So although we have these resources in here, it appears that the formation of the cobalt is at least 200 million years older than the gold. And how do we get to that conclusion? Well, within here, you can see cobaltite, this slightly weird looking mineral here, and cobaltite is a cobalt arsenide. We have pyrrhotite, chalcopyrite, and there is gold that you cannot see. We have two styles of mineralization. There is a potassic iron style of mineralization, and this weird one that we talked about first, the magnesian iron host. The magnesian iron host looks like komatiitic volcanics. Well, at least it has olivine fractionation, because when you look at the nickel data, you can see this beautiful fractionation trend correlated with magnesium that looks like olivine fractionation in a mafic rock. And in fact, when you go along strike, you find these weird magnesium mafic volcanics. And one of the bizarre things about these Finnish so-called orogenic gold systems is that they have this strange association. And I would argue that the association is actually a bit false, because it relates to two processes. It's a bit like the Mount Isa copper ore body, or if you're in the Richard Lilly camp, the lead zinc ore body is there replacing something earlier. So when you put all the geochemistry in one bucket, you end up with something that's not typical. However, if you pull it apart into the different stages, you discover that it's not as messy as you think. So if you know about orogenic gold systems, they often come with bismuth, telluride, selenium, and arsenic. And I would argue that this system here is a classic sort of late orogenic gold system with those characters, but overprinting a strata-bound ore deposit or strata-bound mineral occurrence. There is lots, whoops, and I'll get back to that. There is also lots of scheelite. It's working in, we have to drill in winter up there, so being able to turn out the lights, place goes black. So turning on the black light was perfect, because you could actually tell spatially where you were from the scheelite distribution. So there was scheelite all over the place within these rocks. If you go back now to that earlier image with the cobalt data added, you will see that there is, a relative correlation with the cobalt. So relatively high cobalt, but not spectacular, nothing like the copper belt or anything like that, but significant if you're actually going to dig it up and process it, because throwing it away is a huge waste. If you take the top tray here and put it on the hyperspec machine, you will see that there is a mixture of albite and quartz. There is one white mica and a second white mica. You will also see VG written here. VG, visible gold. And you will note that the visible gold is attached to this brown secondary white mica. What you actually discover is that One white mica here, this one here, is the metamorphic white mica that has been to amphibolite facies, say 400 degrees or something like that, or maybe slightly lower. The other white mica associated with the gold is much lower temperature, is a fangetic white mica that is only sort of 250 degrees. So the classic sort of gold associated white mica temperature. Normally in the white mica world, in spectral world, people go and see cold rocks that are heated up and you produce this fangetic white mica. But here, because the host rocks were already high grade or medium grade metamorphic rocks, they were actually slightly cooled down by the hydrothermal process that formed the gold. And you can get as fancy as you like. And this was very early, largely from the hand lens, but it does say some important things, that on the outside of the system, it is oxidized. So our words were pink is bad. If it's pink, it's oxidized. We're not going to get mineralization. We see all sorts of minerals here associated with the mineralized zone. And you see a little bit of low temperature galena and sphalerite outside the system. So in terms of predictability about where you are when you're logging, it was relatively good. But trying to put together a resource model when your geological interpretation looks like that was interesting, you could say. The cobalt grades do tend to hold with the red here. But note, if I look down here at this one in particular, the gold trends, even though you saw that last image like that, the gold trend is almost linear. There is only one way, if you're a geologist or a structural geologist, to try and make that happen, and that is to have an intersection with a subvertical structure of whatever's underneath. And that will actually give you a linear trend in plan view like that. So why and how does that happen? Well, if you go and sit in the hanging wall, there are a whole bunch of albitites alteration sitting immediately above the mineralization. And if you measure all of the quartz sulfide tourmaline veins, there's that tourmaline again, in the hanging wall, they actually have this trend of, or strike of 159339. So they all sit in exactly the same orientation as this gold trend. So there are a bunch of subvertical veins, quartz sulfide, slightly anomalous in gold with tourmaline, that sit in the brittle hanging wall. Not only that, there are a whole bunch of these really weird magnetic lows here. And if you know anything about magnetics, and I know only enough to be dangerous, in this world, these rocks are, say, 1.8 to 2 billion years old. You would expect most of the magnetic materials to recrystallize back to the current field. However, these are all magnetic lows. They all have their magnetic vector pointing down. In other words, they are reverse remnant magnetite. So you say, oh, wow. Yeah, that's just like the magnetic stripes in the ocean. However, these rocks are polydeformed, and the rocks at Rhea are upside down with respect to the rocks at South Palokas. So the whole sequence is actually folded like so. What that actually means is that the pyrrhotite gained its current field post-folding, because everywhere it points down. So it gained its current magnetic character post isoclinal folding, post-deformation. Just out to the north are a bunch of tourmaline-bearing porphyritic rocks and tourmaline-bearing pegmatites. And from the gravity data, you can actually see the buoyancy tops, and you can actually see it in the magnetics from the aureoles, dipping down underneath these rocks. Those tourmaline-bearing granites have the same boron isotopic ratio as the tourmaline in the veins and in the mineralisation. They are also 1.78 billion years old, dated from the zircons within them. There are molybdenum ages from within the mineralisation, which also match that number. If you try then and say, okay, that's messy because we have all these deformed rocks and the cobalt grade appears to go all over the place, but the gold goes in a straight line. That implies, again, that there is a contrast between the formation of the cobalt and the gold. And if you get down to the nitty-gritty of sulfur isotopes and laser ablation ICP-MS, controlled by really good petrographic observations, you can see that there is cobaltite within the foliations, there are pyrite within the foliations, and there are pyrites within late structures. And those pyrites within the late structures preferentially contain some metals. So we would argue that there are early pyrites there that are pre-peak metamorphic and have recrystallized, and then there are late pyrites that are post-fabric, and they actually take on a different set of elements to the other ones. Now, one of the issues here is that cobaltite is not the only cobalt mineral. So when we start talking about cobalt grade, I'm not talking just about cobaltite. Cobaltite, cobalt arsenide, cobalt grade is hosted within these folded units. Near the high-grade gold, we see more cobaltite, and away either side, we see more lineite, which is a cobalt sulfide in the same way that magnetite is an Fe2 plus, Fe3 plus oxide. So it's strange, but the cobalt minerals, cobalt geometallurgy, is dependent on the gold. And in fact, when you look at the arsenic data, there is only a couple of rocks that actually contain arsenopyrite, even though there is thousands of ppm sometimes of arsenic in the rocks. All of the arsenic has combined with the cobalt when it came in with the gold to produce cobaltite. In fact, there wasn't any free cobalt, wasn't any free arsenic around to produce arsenopyrite. It nearly always mixed with cobaltite, which is a little bit annoying because it's not the best mineral for cobalt processing, but it's better than some. And we've recently been going down to the nitty-gritty micron level to try and look at how these sulfides actually fit within these fabrics and foliations and how this whole story might have evolved during deformation. I suppose what you can say is that even at this scale, it is still hard to make this sort of linear gold story work because the gold grades mean that you don't see enough gold grains generally to get a story out of this. So the cobalt concentrations tend to be strata bound within the layers. Gold is commonly linear. But because arsenic comes in with the gold, cobaltite parallels the gold trend. So when you go out and do a block model, you end up having to muck around with each block and try and determine how much cobaltite and how much lineite might be in each block when you're looking at the recoveries. And so the story is that way back here at about 2.06 and older, the evolution of this basin was dominated by oxidized basinal fluids that were hitting a reductant. And those basinal fluids were carrying molybdenum, vanadium, cobalt, copper, uranium. And they were hitting the reductants that were essentially sulfidic stratabound units within the sequence. And there was a period of metamorphism and deformation, and then there was a significant period of post-orogenic granitoid emplacement that was the heat engine for much of the mineralisation that we see across northern Finland. And interestingly, when you go across the whole Paleoproterozoic and start looking in Brazil and the Tanami and all of those places and South Dakota, there is this constant debate about whether or not these gold systems are post-orogenic. But when you actually look at this 1.75 to 1.8 billion year bracket, there is lots and lots and lots of gold. And lots of those systems occur where there is intersections with reduced sulfidic units. So relationship to the host, but a contrast between the depositional age and the formation of the gold. Thank you.
All right. Thank you very much, Nick. Very interesting presentation. It's amazing the journey that you've been through from nuggety gold to try to understand the whole system using a lot of different technologies. It's quite an amazing story. So I'll open some questions in the audience. Oh, Rick.
So what's controlling the extreme plunge of the ore? You know, they really look like they're super, almost needle-like ore bodies. Are they following hinges or stretching lineations?
So what tends to happen is that the sulfide zones tend to be concentrated into D3 hinges. And those D3 hinges concentrate the stratabound nature. And you can actually see in some places, unfortunately, the gold trends raking across those fold hinges. And as soon as you get out of the reactive zone, all you get is veins with no gold. And so, exactly. And in that image just prior, so in fact, I've got a couple of things just in case sitting on at the back here. So in this hand-drawn diagram up here, in these fold hinges, that seems to concentrate the sulfides. And in that work just with SciAb, with all of those complex geometallurgical diagram, you actually see that, and you see sulfide reactions going on into those fold hinges. And then it certainly appears that the gold veins come across that. And so when they are subparallel to that, you can get 900 meters of down plunge, and other places it's a bit short. And you do see it stepping across as on echelon stacked small hinges. In fact, so there's a discovery at South Palokas this year where they've gone down now. Now there's 3 different lenses of this material.
Any questions? Oh, Tom.
So, Nick, did you say there was cobalt coming in with the gold as well, or do you think all the cobalt was pre-existing and it's just been
altered to cobaltite because there's arsenic coming in with the gold. Is that
Correct,
Okay,
correct.
cool.
So I think the gold is the strata-bound early oxide fluid in the same way that the copper belt oxidized fluid hitting a reductant with minor alteration. I mean, these rocks, they're full of the basement rocks are full of stromatolites, red beds. And then if you go up and you see these amazing oil-bearing, essentially 2.06 oil-bearing rocks, and you go to the Russian side, it's called shungite. There's actually, you can buy it in shops, it's amazing, where that's about 90% carbon. And when you look at that, there are tiny flakes of molybdenite in there, and you can date those molybdenites in the unmineralized stuff at 2.06. The flaky molybdenite within the mineralization comes out at about 1.8.
And what's or is it an orogenic event at 1.78, or is that the?
Yep, I think so. And certainly the great work that Dave Sally did in helping to discover the Ikari deposit up to the north are all in 1.78, 1.8 fracture sets. And it's published, so I can talk, it was in a press release. So basically the current exploration is to say, well, we would get much better gold if we found a big 1.78 aged structure intersecting reactive rocks than being in the situation where you only get the small linear volume because of the subvertical or inclined sort of interaction of the two surfaces. So it doesn't help that the host rocks dip at about 34 degrees, so therefore the plunge is 34. It doesn't give a bigger volume. So there are other places where it'd be really worth going. And if you go to Kirttila, which is a complex age, and I'm not really sure how to interpret it, slightly older, but that's also caught up in these weird organic rocks, lots of black rocks. And then of course the metallurgists in the plant hate it when the shungitic sort of non-structured carbon starts coming into the plant. And you can actually see these rocks as conductors and things all over the place. They're really, really weird rocks. And especially when they get to amphibolite facies. Wouldn't be a bad place to go looking for graphite where it's higher grade to the north.
Thanks. I have a question, Nick. So you show like all those different mineral associations and fluids that interact, and you've been through this journey. I know it's 9 years or 10 years. I don't know how long. If you could come back to the past in some ways, tell like, oh, to understand better the system, I should have done that before in terms of analysis or using technologies. What would you do differently? Or before?
I think we would have done more measurements on the drill core to, I suppose, speed up the geophysics, the rate at which we did the geophysics. It took us a little while to realize how the geophysics actually worked. So, so you see it in the, you see the pyrrhotite conductivity in the VTEM data, and there are now when you did ground EM and did the loops, you could much better position the location of those. And now they're doing much better work with multi-layered conductors to help with the drilling. So we probably could have done a bit more off-hole work. But one really good thing on the other side that we did is we got thin sections very early. We understood what the fabrics were. We knew what the mineral compositions were, and the recording of the data was really consistent. So the actual logging, and I mean, Craig's been there as well, the logging and the treatment of the drill core is particularly good. And so being able to use that data and match it with new data. But this whole latent straight story, I have to tell you, I wrote on the aeroplane going to PDAC when I realized from the late dates and how the geophysics worked that that was the gold trend, and we designed a hole to drill 90 meters down plunge, which is a big step out for a gold project, and smacked it right there and got a really good intersection. So that was the moment where we knew that that sort of predictability actually worked. But, you know, good quality logging and using the data is a key, and perhaps bringing in more geophysics. We had some problems with access, and of course you can't walk on water in swamp, so you need to ski in winter and so forth. And winters, I mean, I know the Finns say that, you know, there's no such thing as bad weather, only poor preparation, but it is pretty cold out there skiing at -30 and trying to write in your notebook and do all that sort of stuff. The drillers up there are fantastic, but you've got to heat the water to keep the water up to the rig and all of those things. So it's tough environment, and it's a bit like parts of Canada, short-term work. So you do get lots of time to think very clearly about all the data you've collected. But yeah, it's interesting work, that's for sure.
Thanks. Another. Great.
So there's a suite of intrusives that are coeval with the mineralization. So you're saying 1.78.
Yes, 1.78.
And I guess when you were talking about the fact that you had this whole folded sequence where the remnants was an overprint of the folded sequence.
Yep.
It reminded me of the Dameron origin, where you get the same sort of thing in the the oxidized part of the sequence, the conformation, where you can see refolded folds that are all remnant, and it's like a thermal overprint that's just kind of baked in a later remnants. But that's not my question. My question is more what do you think was the influence of the intrusives in this case? Were they just around and part of that same kind of part of the deformation history, or did they actually play a more important role in the localization of the mineralization?
I think they're associated with the heat engine. The way in which the distance from them, so you get quite brittle. So over at Rumpus, it's quite brittle, and you get the tourmaline in the fractures. You're relatively far from the nearest one we could work out. You actually see a contact aureole, which is a magnetite out and muscovite out reaction around these things, even when they're buried. And we think from the data that they're buried 1 kilometre down plus. So I would argue that they're part of the heat engine, and I mean, they may be part of this very late sort of 1.78 minor deformation. But there's open space textures and stuff like that just to the south, so it looks pretty shallow. I mean, the temperatures from the fluid inclusion data, everything is, 2 or 3 kilometres, 200, 250 degrees. So it looks very shallow. And it sort of does your head in as a metamorphic petrologist to be thinking about those sort of weird sort of epithermal type temperatures when the host rocks are in thermalite facies. So yeah, largely heat engine, I think. But we see the boron isotopes, all that sort of stuff being identical from one to another.
Okay, so we have one online question from Marcus. You mentioned that you thought originally that the albertites and calcsilicates, etc., were evaporitic, but you have since changed your mind. What is your current thinking?
So I had thought that the weird magnesian rocks were evaporitic, but I think those are magnesian mafic rocks. I think there are early albertites, Marcus, but there are also these beautiful white albertites that are in the hanging wall above Raya, where you can actually see graded beds disappearing into the albertites, and you can see them being much whiter around quartz sulfide tourmaline veins. So much like other places I've worked, and I seem to have spent a career in albite rocks, those albertites weren't very albitic at the start. There was quite a bit of mica in there, but all of that was destroyed in the hanging wall that had the brittle veins that host the brittle veins above the mineralisation. So multiple stages up there, and certainly early albitite, absolutely. And there's pink, just to do your head in, there's pink albertites, there's white albertites, there's pink K-feldspar rocks, and there's white K-feldspar rocks. So if you don't use the XRF or something like that, you don't know what they are.
All right, there is another online question, but I think we're a little bit out of time. So I'd ask everyone to thank Nick again for his presentation. Thanks, Nick.
Here.
Next week we have Rangy Joe from the School of the Environment at the University of Queensland talking about advancing geochronology and mineral chemistry to support the mining industry. So hope to see you all there. Thank you.